So, welcome to the course on architectural design of ICs. So, in the last class we are seeing the sequence detector example. Okay. So, in sequence detector example we have to detect the corresponding sequence of 1101. Okay. So, what we did is that first we have developed the finite state machine which will detect this sequence 1101. Okay. So, once we have developed or once we have actually this draw the corresponding finite state machine, and finite state machine as we have to that means detect this 1101 sequence. So, depending on that only we came to this finite state machine. If this sequence is different, so at that time this FSM will be also different. So, after that as we have to detect the sequence of 4 bits. So, that is why we are having 4 states. Now, what we have to do is that we have to encode this 4 state by this S0 to 00, S1 to 01, S2 to 10 and S3 to 11. So, as we are having 4 state, so we need 2 flip flops. So, using 2 flip flops we can easily, that means build the corresponding circuit of it. Now, if I have to detect sequence of 5 bit, so at that time the minimum requirement of this flip flop will be, so at that time there will be 5 state. So, 5 state means at that time we have to consider 3 flip flops for designing the corresponding circuits. Okay. So, and then for this example we will be using T flip flop for designing the circuit. So, now how to, what will be the logic, how to know that okay, this is the logic which will be implement this particular sequence detector. So, now next what we have to do, we have to draw the corresponding excitation table of T flip flop. So, from this T flip flop excitation table, so as we are having this S00 and like here this S0 is 00 and it is having 2 branch, one for 0 another for 1. Okay. So, then if I consider okay, this is 00 00 for state 0, if the input is 0 then it will go to the next state or it will remain in the same state. If it is depending on this, when this is 00, that means the input is 0. So, at that time the output is 0 and again it is in the, it remains in the same state. So, that means the present state is this 00. If the input is 00, the next state will be also of 00. Okay. And then when this present state is 00 and x, that means the input is 1. So, at that time the next state will be going to the S1. So, which is 01. Then for this state S1 which is 01, if the input is 0. So, at that time it will go to next state which is corresponds to this, it will go to S2, S2 is nothing but this 10, whether this input is 1. So, at that time again it will remain on the same state which is 01. Then again for state S2 which is 10, if it finds that okay, the input is 0. So, again it will go to start from S0 depending on the corresponding that FSM what we have drawn earlier. So, 00, then if it is 10 and the input is 1, then it will go to the S3 state which is 11. So, something like that we have just gone, we have just derived these particular equations from these tables from the state diagram or this FSM. So, actually depending on the excitation table of T flip flop, now for this next present state to the next state depending on this excitation table, now we can actually derive, as we have to develop or we have to design the circuit using D flip flop, that is why we have to use the excitation table of T flip flop. Okay. So, depending on this, now what will be the present state, what will be the next state, depending on this will be its the value of the excitation table of T flip flop. Okay. And what is the output? The output is here, you see, for all this is 0, only when this S3 finds its input as 1, then only it produce the 1. That means, for this particular, for 1 1 1, the output is 1, in rest of the case all are 0. Okay. So, when this Q1 is the present state 0 to 0, T flip flop, this is 0, 0 to 1, this is 1, this is 1 to 0, again 1, 1 to 1, this in T flip flop this is 0, 0 to 0, 0, 0 to 1, 1, 1 to 0, 1, and 1 to 1, 1. So, in the for Q2, so 0 to 0, 0, 0 to 0, 0, 0 to 1, 1, 0 to 0, 0, 1 to 0, 1, 1 to 1, 0, 1 to 1, 0, 1 to 1, sorry 1 to 0, that is again 1. Okay, that means, the Q1t to Q1t plus 1. So, this corresponds to the excitation table, this value we came from the excitation table of T flip flop. Okay. So, once we have developed this will be the corresponding output. So, we need to put it in the Carnot map for the logic simplification. Okay. So, now whenever for this Q1, Q2 and for x, whether that is 0 or 1, so we can get the corresponding T2 3 table, one for T2, one for T1 and one for this x, which is for O. So, this is for O, where only for this 1 1 1, this is 1, and for this for T1 we are having this Carnot map of this, and for T2 this is something like this. So, depending after placing or after designing this Carnot map, we will get the corresponding logic of T2 as Q2 dash T, Q1 and x bar. So, T2 means this one. So, Q2 bar plus Q2 bar, Q1 and x bar. For this is Q2, Q1 and x. For this is Q2, Q1 bar, x bar. So, T2 will be Q2 bar, Q1 x bar, Q2 Q1 bar, x bar and Q2 Q1 x. For T1 this is what? This is Q2, this is Q1 x bar plus Q1 bar x. Okay. So, Q1 x bar is for what? Q1 x bar for this one 1 1 and this is common for 0. So, here Q1 and x bar, and for this it is Q1 bar x. So, this is nothing but Q1 XOR with x, and for the output, the logic is Q2, Q1 and x. So, once we derive the equation of O, that means this is the output of T1 and T2. Now, if we draw the corresponding circuit based on these three equations, we will get the output as this one, and then the T2 and the T1 will be the inputs to this particular T flip flop, where that means this is for T2, which corresponds to this particular equation. This is the T1 input, which corresponds to the XOR gate, and finally, we will get the sequence detector. Now, these particular circuits will work as a sequence detector of 1101. Now, if it is been asked that okay, you have to detect one different sequence. So, at that time, starting from making the state diagram and then using the state that means this excitation table, you make the corresponding that means Carnot, then again using the Carnot map, you will get the expression for T2, T1 and the output, and then you draw the corresponding circuit of it to get the sequence detector of the corresponding whatever has been asked to detect the proper sequence. So, this is the steps how we basically design one sequence detector. Okay. So, then again we will see, actually initially we have seen that multiply by 2 clock, multiply by 2, multiply by 4, multiply by 8, that everything we can do. Now, we have to design divide by 2 to the power n. Okay. So, divide by 2 to the power n, let us consider now n equals to 1, that means divide by 2 counter. So, how we can do? We need one counter, this mod 2 counter, which will only count 2 clock pulse of the clock signals. So, this, that means when this clock is 0, the count is 0, the clock pulse is 1, and when this is 1 1, the clock pulse will be at 2. So, how to design? Only by that means D flip flop, only one single D flip flop, you can make the divide by 2 counter, sorry, divide by 2 clock generator, or if this is nothing but this mod 2 counter. So, what is that? The Q bar is basically input to the D. So, this is the reference clock. So, reference clock. So, initially what will happen? Initially if this is 0, then whenever it finds the edge, so Q 1 will be 1. So, it will be just gone to the next. So, when it finds that okay, Q bar equals to 1 and this is 0. Okay. So, at the time, at the very next edge, what it will be? The Q, now this is the D input which is 0. So, now this is 0, this will be 1 initially. After that, again when it finds that next edge, at that time what it will be? It will be just 1. So, Q bar will be, Q will be 1 and this Q bar will be 0. So, this Q bar will come over here at the D. So, at that time it is 0, then again it is 1, then again it is 0, then again it is 1, then again it is 0. So, something like this, this particular things will be toggling. Okay. So, toggling depends on the corresponding clock edge. So, as it is finds this data is changing for one particular clock. So, that is why if you see this is nothing but the divide by 2 clock. Okay. Now, if I have to make the circuit of divide by 4 clock. Okay. So, whenever this n value is 2, so at that time I have to divide the clock by 4. So, how we can do? That means, at that time the corresponding signals will pass 2 clock cycles to make it. So, at that time what will be its circuit? We need, so initially for divide by 2 we need mod 2 counter, here we need mod 4 counter. So, mod 4 counter means this the last count will be 1, this 1 1 0. Okay. So, 1 1 0 means here you see initially this Q 0 is connected to D 0 and this Q 1 is also connected to the D 1 of this. Okay. Now, in case of the divide by 2, only one the T counter, that means this one T flip flop is enough. Now, in divide by 4, if you pass this divide by 2, again another D flip flop. So, then again it will be divide by another 2. So, now it will make as, or now it will become as divide by 4 clock. Okay. So, then if you just see that okay, this is the Q 0, this is the, that means reference clock. Now, this is the Q 0, then this is the Q 1 and Q 1. Now, if you just that means if you just make this, then this is the output, that means this corresponding Q output is now the clock. That means, whatever this divide by 2 clock, divide by 2 clock. Now, if I pass to the next state T flip flops as the clock, so then it will be the output, D output will be nothing but the divide by 4 clock. here you see this is the reference clock. So, from this Q0 we are getting this divide by 2 clock, then that is the clock for the second T flip flop. Then again this will be again divide by 2, which will make the divide by 4 of this reference clock. Okay. So, then again divide by 8. So, how you can design divide by 8? Divide by 8 means it you will be having 4 clock pulse, sorry 4 here, and then again 4 for the lower, that means for 0. So, what you can do, you will be having this, you will be at that time what you can do is that for you will be having the clock signals, then you will be having this, then the output from that it will be just as the clock signals to the next one. So, this is the reference clock. Okay. So, this will produce divide by 2. Okay. Then again if I connect this here, so this will produce the divide by 4. Now, this again this if I connect this to particular clock to the third one, and again this is here. So, now this is divide by 8. Okay. So, that means after the first T flip flop it will be divided by 4, then again the output from here, that will be the clock for the next one, it will produce divide by 4, then again that is the output from that, that is the clock to the third one, which will provide you the divide by 8. Okay. So, in this manner we can you can actually this develop divide by 8 as well as divide by, here you see this is nothing but this Q0 is connected over here. For the first flip flop you are getting divide by 2, for the second flip flop you are getting divide by 4, for the third flip flop you are getting divide by 8. So, the same manner if you want to divide by 16, you will be having, or you need 4 flip flops. So, 4 flip flops, how they will be connected? So, in the same manner, now the output of this will be connected to the that another flip flops over here, where this is the clock, okay, and the output will be something like this, which will produce, this is divide by 16, okay, and this is, here is the reset signal which is coming. So, all this is nothing but the D flip flop. So, D flip flop, that is why this Q bar is connected over here. Okay. If you use T flip flop, then at the time this with the this if you connect, then it will be okay, no problem. So, in this manner we can design any of this divide by 2, divide by 4, divide by 8, divide by 16. So, this is very much easy. If you need divide by 32, you add another flip flop, it will be again divide by 32. Now, suppose we have to design that divide by 3. Okay. So, at that time that is not that much easy, just like whatever we did in case of divide by 2. Whenever it is power of 2, divide by power of 2, at that time you connect the stage, you increase the stage, you will get the corresponding output. But in case of this divide by 3, that means when the power is not of 2, at that time you need one for divide by 3 clock requires one mod 3 counter. Okay. So, and it can be constructed using 2 flip flops. It has four possible states and it needs only 3 states to be used. Okay. So, what are these 3 states? The 3 states are these 100, 101 and 110. Okay. So, now if you just make this, so at the time what it says that observe the output of the second flip flops. that for these two case the Q1 is all time it is 0 and here it is 1. So, that means this is the terminal count. Now, based on that, if you just connect this like, so you are having the, in case of only mod only by 2 at that time what is there, that means you have to connect this to here. Okay. So, whenever you are having this, that means finally you are having that up to mod 3. So, that means mod 3 where from you will get, mod 3 you will get from the corresponding the second flip flops output. So, here 1 and this one, if it is ANDed and it is the input to the first flip flop, then you will get the corresponding that that means the divide by 3. But here I need the divide by 3 and with 50% duty cycle. Okay. So, 50% duty cycle whenever you need, so at that time you need one extra of this particular gates which is required to make the duty cycle of 50%. What is the logic then? Then you have to OR with the this and the corresponding third flip flops output. If you do that, then this circuit will give you the divide by 3 with 50% duty cycle. So, here you see, if you see that means timing diagram. So, this is the reference clock. So, the Q0 is, so the Q0 will be dependent on what, this Q0 bar and Q1 bar. So, depending on that the Q0 value is will be something like this, and what is the Q1? Q1 is nothing but the Q0, which is 1 bit 1 clock cycle shifted. So, this is nothing but this, okay. And then you will be getting the corresponding Q. Okay. So, what is this Q? Q is the output from the third one. So, Q is dependent on the Q1. Okay. So, now Q1 again that is shifted. So, Q1 is shifted means depending on the corresponding this flip, that means the flip flop delay, it will be just after, that means Q1 is now here, Q is also shifted by the clock to Q delay. Then the output is basically the OR of this Q1 and Q. So, Q is this one and Q1 is this one. So, whenever I need, so at that time as this is OR. So, for this particular this will be 1 and in these two both of them Q1 and Q both of them are 0. So, the value will be 0 over here. Then again at this okay, not at this Q1 and Q0, Q1 based on the values of Q1 and Q, you will be getting the divide by clock 3 output as this one. Then again at this you will be having both of them are like 1 1. So, at the time again you will get that output as 0. Okay. So, if we do this, so based on this Q1 and Q, you will be getting the corresponding divide by clock 3. Now, as you see that okay, this is basically the sequence is now that okay 1, 2 and 3. Okay. So, the 3 clock divide by 3 means the total it requires 6 clock cycles. Okay. So, how 3 clock cycles, sorry, 1, 2 and 3. So, 1, 2, 3 clock cycles it requires 2 which will be produced by this divide by clock 3 output here from here. Okay. So, this is the circuit for divide by 3 with 50% duty cycle, and what I said is that you have to use this extra gate to make it 50% duty cycle. Okay. Otherwise, you do not have to use that. Now, again another actually circuit I need, which will be using this divide by 5. Okay. So, a divide by 5 counter request can be developed using mod 5 counter in similar method. To get 50% duty cycle output, one more flip flop is added and it is negative edge triggered, and pass the output of the second, pass the output, that means depending on this Q1 you have to pass the corresponding logic. So, here is that means now this is the circuit is something like this. So, here in this you are basically calculating, this is nothing but the mod 5 counter. Now, you are having one extra this delay extra amount of these gates, which will produce this divide by 5 with 50% duty cycle. So, what is that? That means, here it will be QB and QD, QB and QD. Then depending on this QB and QD, now you will, whenever we will OR them, at that time I will get the corresponding function something like this. So, that means, here actually 1 at this particular edge 1 and 0. So, 1 within this is 0 0. So, it is 0. So, we will get this the divide by 5 with 50% duty cycle based on the mod 5 counter over here, and then the additional XOR gate additional OR gate to make 50% duty cycle. So, and here you see actually we are having 1, 2, 3, 4 and 5 clock cycles. So, that is why this, and this is the generated output of divide by 5 with 50% duty cycle. Okay. So, now this is the technique for designing any, that means the clock divider circuit by not in the power of 2, by 3 or by 5, by 6, by 7, by 9. So, we will see up, that means today we have seen divide by 3 and divide by 5. Again in next class we will see how to design the other that means clock divider circuit, where we can use different value like 6, 7, 9, 10. So, something else, how to design them, and with all of them with 50% duty cycle. Okay. So, thank you for today.